Can you tell me how a lawnmower engine works?
Of course. We're about to tell you all about the lawnmower engine and our fluid mechanical dissection. First, we will pull the cord to start spinning the engine. Manually spinning the engine is necessary so that it can start sucking in air and fuel using a carburetor. A carburetor is a device used to mix air and fuel at the correct proportion needed to make our engine run. It utilizes a venturi to generate a pressure difference that sucks up fuel into an airstream that is sent to the intake manifold. A venturi generates a pressure difference by constricting fluid flow through a narrow region, causing the fluid speed to increase and the pressure to decrease through a smaller area.
When the choke valve is opened, air at approximately P atmospheric enters the carburetor, which has a converging-diverging geometry. The air accelerates through the neck region, which has a smaller cross-sectional area, and increases in speed in order to satisfy conservation of mass. Pressure at the neck region is less than pressure at air at the entrance of the choke valve. This can be explained by the Bernoulli equation, which shows that pressure along a streamline decreases as fluid speed increases. The Bernoulli equation only works here for fluid flow with a high Reynolds number and for Mach number less than 0.3, or the incompressible flow approximation. When the throttle valve is open, pressure downstream of the venturi is a lot smaller than pressure at the entrance of the choke. This pressure difference causes fuel to be sucked out of the tank, which is approximately atmospheric pressure, and into the airstream. The mixture can then flow through the throttle and to the intake manifold of the engine. When the throttle is closed, though, pressure is roughly P atmospheric throughout the carburetor and minimal fluid flow occurs.
Our first assumption was to assume a Mach number of less than 0.3, which simplifies our calculations. This is a reasonable assumption because the flow rate is not that high. This allows us to use the Bernoulli equation. Then, we can assume gas is aerosol in the mixture, which allows us to assume that the density of the mixture is solely the density of the air because the volume of the gas vapor, if it is aerosol, is very low, so the density of the mixture is mostly air. We also assumed conservation of mass, that the pressure at the inlet is atmospheric pressure and the outlet is atmospheric pressure divided by 3. We also assumed no flow separation, as we are assuming this is an ideal carburetor and that there are no viscous losses. These are some values that we measured in the lab when we dissected our engine. Also, these are the values we obtained from the engine specifications of our model and the densities we looked up. We chose to do 4 different control volume analyses, one before the throat, one containing the throat, one after the throat, and one encapsulating the gas intake. The red control volume has air, the green and purple one has an air-gas vapor mix, and the blue one has liquid gas.
The velocity at the exit of the carburetor is determined by applying conservation of mass to the crankshaft piston. We found that the RPM of our engine was 2,500. Using calipers, we measured the stroke length of the piston to be 0.048 meters. This is the control volume analysis we use to calculate parameters before the throat. We use Bernoulli and conservation of mass concepts here.
This is the control volume analysis we use to calculate parameters after the throat. These are the initial parameters we used in our calculations. Using a MATLAB script, we were able to calculate velocities at different points in a venturi. Our analysis tells us that flow is fastest at the throat. This makes sense based on what we learned about rocket nozzles and the area-Mach relationship. Area is smallest at the throat, and velocity is the fastest there. It also tells us that pressure at the throat is less than atmospheric pressure. This relates to the Bernoulli equation, which tells us that as velocity increases across a streamline, the pressure must decrease.
All of our equations were heavily dependent on area and density, so the geometry of the venturi as well as the fluid choice are very important. In order to optimize performance, we want to reduce the risk of flow separation by having the throttle of the carburetor diverge gradually as opposed to having sharp angles. This is similar to what we observed in the vacuum venturi lab. We can also have a smaller exhaust area than inlet area for faster fluid flow into the combustion chamber.
First, air and fuel enter the carburetor and into the combustion chamber of the engine. Atmospheric pressure forces the air-fuel mixture into the cylinder bore and the piston moves downward. Next, intake valve closes and the piston travels upwards, compressing the air-fuel mixture between the piston and cylinder head. Then, the piston reaches the top of its travel. A high voltage is created in the ignition, and the spark plug discharges the voltage into the combustion chamber, igniting the gases and forcing the cylinder back down. Lastly, exhaust valve opens, and as the piston travels upwards, it pushes the spent combustion gases out of the exhaust. Piston returns to the top, exhaust valve closes, intake valve opens, and the cycle starts again.
Then the shaft rotates the cutting blade.
My grass is too long.
Fuel and air mix, then combust.
Venturis are cool. Oh, I get it now.